Okay, this is the third entry into this podcast about Chapter 9, and we're going to be learning about MO theory. So I'm going to advance to that slide, and we're going to start learning about MO theory, molecular orbital theory. See, some aspects of bonding can't be explained with Lewis structures and can't be explained with VSEPR theory, and we need this MO theory. I did a little erasing there. Sorry about that. One of the things that caused MO theory to come to be was oxygen. The VSEPR theory suggests that oxygen would not react with a magnetic field having unpaired electrons, but it does. And it's hard to understand the coloring of some molecules without MO theory. And so there are different purposes, that require the MO theory. Okay, so the main idea of MO theory is if you took two hydrogen, here's one and here's another, and move the two hydrogens closer to each other, one of two things could happen. They could interact positively, like two waves coming together and growing a bigger wave, and that's shown on the bottom part of the diagram, or they could interact negatively, and that the behavior of the electron in the one can cancel out the behavior of the electron in the other, and then you get a node. And in fact, both of these things occur, or so the theory suggests, that when two hydrogens come together, they form no longer, these are atomic orbitals. This is with one hydrogen, but they form together, and we form what we call a molecular orbital. And the one where the interaction is positive is at a lower energy of the one where the interaction is negative. It's reinforcing versus canceling. And so now when two hydrogens come together, they would form a sigma bond. So the positive sigma bond we would call a sigma 1s molecular orbital. And then when they interact such that the wave functions cancel, the star means that this is the canceled section. So we call this other molecular orbital sigma star 1s. And the electrons, now the bottom one is of lower energy than the top one. So if a hydrogen with one electron and a hydrogen with one electron were to interact, we would put the electrons into the bottom orbital, not the top orbital. So I'm going to go ahead and do that by drawing in the arrows here. And I got to draw that one downwards. I'm sorry, I'm not drawing so neatly here. That's not so good, so I'll just erase and fix. Okay. Eraser, there we go. Sorry about the sound effects. Okay, and we'll draw this arrow down. Okay. And this would be a molecular orbital diagram for a hydrogen atom. So, if the interaction between the two hydrogens is like constructive interference, you get a lower energy. And this sigma, without the star, contributes to bonding. When electrons go into sigma orbitals, they contribute to bonding. When electrons go into sigma star orbitals, they contribute to non-bonding or anti-bonding. If the two waves functions from the hydrogen atom interact destructively, you get a higher energy molecular orbital, and it's considered to contribute to non-bonding, and we call that an anti-bonding molecular orbital. Okay, and we're going to learn how to draw these diagrams. And what we like to do is put the two molecules that are going to bond together on either side of this diagram, and you can put their electrons in before you start. They arbitrarily seem to spin differently in this representation, but the first place they go is the lower orbital, the lower energy orbital. So they're both going into the lower energy orbital. They would not go into the upper energy orbital unless there were more electrons around, and there aren't. We're able to calculate something called bond order. Bond order is when you take the number of electrons that are in sigma orbitals and subtract those that are in sigma star, so in this case it would be 2 minus 0, and then divide that by 2, you get a bond order of 1, and that suggests that a hydrogen atom would have a single bond. Well, let's look at this in a different setting. But before we look at it in a different setting, here's the calculation of bond order. It's the bonding electrons minus the non-bonding electrons divided by 2, and that equals a bond order of 1. In the case of helium 2, which doesn't that just look weird looking up there, this thing here, it doesn't form at all. And so if you put 2 electrons from helium and 2 more electrons from helium, the first 2 would go down here, and the next 2 would go here, and there'd be 2 bonding electrons and 2 anti-bonding electrons, and that suggests a bond order of 0. And we know, or we don't know, that helium, we know nothing. We're just beginners here learning chemistry. But helium, diatomic helium, does not exist. So that seems to make sense. Now, the same thing sort of happens with the p orbitals as well. Okay, there are 2 ways that p orbitals can interact. Okay, now if we take, let's first look at the ones that are lined up with each other, these guys up here. Okay, they are along the axis. This is the line connecting the 2 nuclei. And if we were to move these closer to one another, since the bond is along the line connecting the 2 nucleuses, this would be a sigma bond. Even though it's made out of p's can form a sigma bond as long as they're not above this plane or below this plane. And they can interact in the same way and form, if it's constructive bonding, we would call that sigma 2p. And if it's destructive bonding, that means that when the wave function is up and the other is down, this is using your physics very heavily, gang, you get that node in the middle, and that would be anti-bonding. So we're taking the ideas of atomic orbitals and combining them to molecular orbitals. Over here, if this is along the plane directly, the other lobes of the x and y, notice we're not doing hybridization here and forming sp3 at 109.5 degree angles. We're kind of forming these, we're back to the original x, y, and z coordinates, but this one that's above and below this line would interact as a pi bond. Now, if they interact favorably, then you get this overlap. So this type of representation is when as they move closer, they constructively interfere with one another. You get a molecular orbital that looks like this, and we call that a pi 2p. And the same thing down here, pi 2p. I don't necessarily differentiate or worry about the x and the y coordinates so much. They're both not in the plane of the atomic nuclei above and below. And so you get two of these guys. And then if these interact destructively, you get pi star 2p orbitals. So this representation is destructive interference of or combination of the 2p orbitals. All right, so we get this seemingly confusing looking diagram. Even though this topic is tough, it is not beyond the scope, so we have to fight through and learn it. Okay, so I'm going to use the example of two borons combining together. Okay, one boron and another boron. Okay, so what is boron? What element is that? Libeb, it's element 5. Okay, right? So its electron configuration is 1s2, 2s2, 2p1. Yes? Yes. Okay, so never mind the 1s's, because, well, we can discuss why you never mind the 1s's, but they're like helium-2, and they have a bond order of 0, and they neither contribute to or against bonding, so let's ignore them. It's the 2s and the 2p's that are important. So let me draw these arrows in as they are, right? They would be for boron like this, and they would be for boron, the other boron, like this, and these are representations of the orbitals. And then the 2p, you'd have 1 up. Now, I tend to draw these diagrams with the 1 up, but I saw a hint on the previous slide that they like to draw it down, but we'll figure that out. Well, the bottom line is the electrons will go into the lowest, these are atomic orbitals on the outside here, and they're combining together. It's really the same guys, it's the same orbitals, but when they combine together, they form molecular orbitals. So the atomic orbitals from the two atoms will combine together to form the molecular orbital. The two 2s's, the one from the one boron and the other boron, will combine in two ways, constructively and destructively. In each case, the constructive way is the lower one without the star, and the destructive way is with the star. And the constructive way is favored, and that's where the electrons go first, and the destructive way is at higher energy, and it happens second. So I'm going to take these 4 electrons and put them into the molecular orbitals. The molecular orbitals are the same as atomic orbitals in that they can always hold 2. So I'm going to put 2 arrows in here, and then I'm going to put 2 in here. Okay? So I got 4 here. Now I have 2 electrons left, and they'll go in here. Well, they'll both go here. Now, the question that comes to my mind is, how does the spin of this one flip around? And I guess the answer is, I don't really know. I saw that on the previous slide, or about 3 slides back, we represented this as interacting the other way. And maybe if there was a lot of borons around and they were looking, they would find one with a spin opposite, or would wait till it would orient in that position, something like that. But at any rate, we have 4 electrons in bonding orbitals. This is having no star is a bonding, right? So this is, maybe I'll write it down. I'll just put a little b over here. Bonding, right? And this is bonding. Okay, and this is with the star. This is the one orbital formed by destructive interference. This is anti-bonding. Sorry about the bad handwriting. I'm using the mouse and not my little touchpad. That's in school. I'm at home. And So we have 4 bonding electrons minus 2 anti-bonding electrons, so that equals 2. And then you divide it by 2, and we get a bond order predicted for boron of 1. So we've kind of organized the boron molecules into its expected situation. All right, I'm going to stop this podcast now because I'm using a new technology, and save it and upload it, and then we'll continue the rest of this molecular orbital discussion once I've confirmed that I have the capability of saving this screen capture mode, which is, I believe, a little bit stronger than when I simply voiced over. And also, it doesn't have that undulation, which several of you were upset about. All right, so I'm going to stop, save, review. Hopefully this will work out. I hope it does, because I don't want to do it again.